Hello everyone. Hello everyone. So I think uh, it's right time to start. It's 10 a.m. and let me present the screen. So I have shared a link for question answers. Maybe so. Okay. So one thing that we can go through. You can. I'm posting this link on YouTube series somewhere so that everybody can ask questions on the slide so that I can uh, watch these questions. Oops, there's lot many windows open. Let me just put the question slides there so that you can ask your question. Okay, are you able to see this link? You can ask your questions on this link for this video, for this today's tutorial. uh, and let me put that. Able to see this link, you can ask your questions on this link for this video, for this today's tutorial. Okay, I think. Okay, so before moving further, just let me know whether you guys are able to hear me properly. Just type yes in the chat, that would be helpful to me, and then I'll move further. Yes, no, please. Just for the to help me out, please type yes in the meanwhile on the chat. Okay, so I assume that at least one person has said yes. I'll assume that you are able to see and ask questions. By the way, the link that I've shared on chat is the link so that you can ask questions. Those questions will be recorded on the slides. Uh, I found this tool a good tool to kind of run our sessions through. And yeah, okay, great. So I have already put here. And so I thought that we already have gone through one lecture where Zimi helped you out to set up Jupyter Notebook environment on the cloud, on Google Cloud, by setting up a virtual machine and setting up the networking over that, and so that you are able to access it through your browser, and so you can code up your TensorFlow or scikit-learn or other machine learning based programs, right? But before we go further, I just want to take a step back and I thought that, let me put in this way. Basically, I have already shared the slides with everybody of each one of you, and if not, if somebody who hasn't been able to see through the slides, please go to our meetup.com uh, page, and the DS Tele, and there you can actually go there, and I've actually shared the links of that. And these slides will always be in work in progress. This is not that what all the slides are not something that we'll cover in today, but it's a whole set of slides corresponding to the content that we'll cover across this series. Okay. Okay, and also my introduction. My name is Puneet, and I have been into this industry from last around, I mean, overall industry experience is around 8 years, and I've been working on machine learning from the last for couple of years, for around 4 to 5 years, and uh, basis around my back introduction, I was into software engineering roles in the beginning of my career, and then I moved on to uh, particularly into operations and marketing for a bit of time, and then I've grown up as a DBA for a year. I worked as a DBA. I just got the opportunity to work as DBA, and where I learned a lot of things around databases. And then I moved on to a business intelligence analyst role, where I actually got into this field particularly to see the problems from the angle of business stakeholders, or we call decision makers, and that's where I realized that I need to go and take it to next level, considering my experience in algorithms and business intelligence and database administration, and looking across various teams like operations and marketing. And that's where I started moving into data sciences roles, and now I am playing a bit of product management roles as well, so actually see through end to end of any problem statement, connecting every stakeholders from the beginning, from the sales conversions till getting it delivered. So that's how I see data science's role to be for me, and it might be a different journey for you guys who are already into this, or maybe later on in the years to come, who are new basically. Then you might have your own set of roles. It's all about, there's a total set of skills that will cover in this will encompass a data science. So yeah, okay, great. So why we have started this is okay. So this is around all this. What we are doing is under the name of Data Science Delhi. It's a open. We want it's a open community that we have set up just so that we can create a social impact, and also bring in industry oriented practical education, and create a learning ecosystem. And we have recently held workshops in universities, and even we are talking to government stakeholders, possibly for a collaboration where and apart from that, we are also keep holding workshops with industry stakeholders, maybe it's corporate requirement, but again, it's always not for profit. It's only about that. We just wanted to be continue to be as a community support, so that anybody can come, provided that the expertise of different skill sets, and then come and take the lecture. Okay, in a way creating a learning ecosystem. And later on, so any projects, if the government needs help, we can bring people onto that from the community and solve those projects, particularly, I mean, social impact problems, you know okay. um, Later on we'll further redefine all this for in detail. I mean, it's a separate conversation altogether, where we want to actually discuss data science Delhi's vision. But yeah, we we are basically, by holding these workshops, we are actually taking a step one into this direction. Okay. Okay, so basics of machine learning. So that's what we wanted to first kind of cover up today as the first thing. And let me, I don't know whether you are able to see that. Okay. Okay, great. So first thing first, supervised learning and unsupervised learning. The key ML terminology that we'll discuss. Supervised learning. So I'm sure that many of you have already gone through these terms, unsupervised learning again, right? So what is, I mean, in machine learning for a high level, what we can say is that there are two types, right? Although there are multiple types, but basics are like supervised learning and unsupervised learning. Supervised learning is the problem statements where we know our labeled data. We have some labeled data, we have some input, we have some output corresponding to that historically, and now using which we'll be able to build models. I'm sure for the completely newbies to this field, it will be confusing, but just keep going with today's lecture. I'll introduce a lot of terminology, those who are new, but those who are already know about it, it can be a kind of revision for them. And unsupervised learning uh, is something where we actually don't know the labels. What I mean to say is that example of supervised learning. Let's say bay stock markets. I mean, you have continuous data being generated for stock markets, and where the problem statement is that you want to kind of predict what how the stock market movement will be for a particular share of the company, right? But now here you have to build a model. You either you'll have historical data, right? And for which date in the past, yesterday, day before yesterday, or a few days in the past, what was the prices minimum and maximum for that particular share in the past, right? So input, input is that, okay, given a date, and output is what will be the price of the of the stock price, right? What is the stock price? And so this is a supervised learning example, right? Unsupervised learning is something, let's say you have a lot of customers, and you want to identify what are the different types of customer you have. Now here you have the whole customer data, where basically, what is the age, all the demographics, what is the age of the that particular customer, how many times they visit your store or online store or whatever, and how many times they buy, what they buy, and all, and so on. All these details are with you, but you actually don't have the customer type. Customer type can be a regular shopper, let's say, or a very passive shopper, or you know or a customer who uh, have the needs of a more like a the customer who is more alcoholic, let's say, who buy alcoholic products, right? A customer type which somebody as a who is more as a, I would say that a traveler who has a traveler need, so he always buys something related to any travel products, or a customer who continuously comes to your website just only to buy vegetables, or a very very regular customer, and so on. I mean, that's up to you, that how you, based on your business problem, you can define different customer types, but that's exactly not in your area, right? You have to generate it, but you can segment your customer into different types. Okay, different personas, basically, you can also say that. And so that's where unsupervised learning approaches come into picture. Okay. Now comes the new more terminology like uh, basically labels, features, models, training, inference. You will keep hearing all this while we go further. So labels are what is the target variable, whether we are here to predict something, whether we are able to classify something, predict the number of rooms in a hotel in the future, how many those will be booked. So it's like that's the label, right? Or you know whether some a transaction is a fraud or not is a label, right? It's a fraud or not, it's a label. And email is a spam or not, it's a label, right? Or whether your railway ticket will be confirmed or not, it's a label, right? And so on. Features are something that goes as input into the model. um, these are the input variable or the known information that you have, or the known data that you have. The known data can be, okay, given that you booked your ticket, railway ticket, so on so date, and at that point in time how many tickets were available, how many tickets were sold, what type of ticket that you booked, try to book or placed a request for a ticket, and how many tickets you have booked in the past, which from which city you are traveling from to which city you are traveling to. All this goes as input in deciding the label for you, whether your ticket will be confirmed or not, right? And so on. So model is nothing, just like for all the newbies, model is just as equation. It's like y is equal to mx plus c, where x is a features, x is a feature, and y is a label, right? And so then is the you know training. So training is where, just think around that, when you have to build an equation, you have a lot of data, and you fed this data to the equation. Basically ask the system to kind of train you, you provide all this data to, so that the model or the equation can learn from the data and adjust its parameters, you know and so basically why training is needed, so that it can learn through the data and build an equation over it. Okay. Inference is something that once you have built a model, now you want to, you have new data, now you want to predict over it, right? You want to generate new instances, you want to, actually, let's say you, based on historical data, you created this model where which tells you, given certain input variables or features, basically, what, whether the railway ticket will be booked or not, will be confirmed or not. So that's is inference. Okay. And now is a regression, classification, clustering. Again, these are again very ML 101 terms. So what is regression? So regression is where the label is a continuous variable. Okay. So something like how many, what will be the occupancy of a hotel room in the future, on a future date, right? So whether, when I'm predicting this, I'm basically, my output variable will be regression, or how many customers will be coming, visiting in the store at a particular hour of the day. Again, it's a regression, right? Or any continuous variable. What is the given, that particular home has certain conditions, or a particular home has certain features, a house has certain features. What is the price of that house given this date, or even independent of it, right? I mean, considering that this house has two rooms, one bathroom, and all these facilities in this, house, and this house being part of a particular society with certain facilities, you will say, like, what should be the price of this house. So this is a regression problem. Classification is what we discuss around, like email classified as spam or not, and railway ticket confirmation, and even fraud detection, right? Any kind of fraud any kind of transaction is fraudulent or not is a classification problem. And then, or apart from that, you go and apply for a loan to your bank, right? And bank looks at your history, lot of history, and then based on it, it decides whether you have a likelihood of defaulting on a particular loan, and based on that, bank decides to offer you a loan or not. So it's again a classification problem, more like. And apart from that, there's a third type is clustering. Clustering is what we discussed about unsupervised learning. So regression and classification comes under supervised learning, and clustering comes under unsupervised learning. So clustering is like user segmentation. What type of users are visiting my website? The whatever the traffic. So you may think of like I must be collecting a lot of data on, let's say, Google Analytics, Mixpanel. I mean, there are a lot of tools available which capture all the data of the users coming to your website. It might be signed up user, it might be non-signed up user, right? But you still have their fingerprints, digital footprints, I would say, and based on which you'll say that okay, so and so many users prefer to visit a particular page. Let's say you are a you are a a company, a satellite TV company, right? And you are offering multiple channels and gamings and even multiple type of channels. So some users are continuously watching cartoons, and some users are continuously watching thriller movies, and so on. And based on that, once you are able to segment your users into this, and so you can have a recommendation system where you can actually push notifications to your users via email, via call, via phone, and so on, based on what they watch, and so you can recommend new offerings to them. Okay, and let me see questions. Okay, I have a question. I want to implement topic modeling to find titles of the document. Would it be easier to do with Google Cloud? I'm a novice in Google Cloud. Yes, it would be easier to do with Google Cloud. However, Google Cloud is just an enabler. So you have to, we will discuss unsupervised learning in detail. So topic modeling is another use case, kind of. Sorry. Okay. So this was the question by Pushpendra Sharma, and topic modeling is a use case. For example, I mean, let's say there are online reviews being posted on an e-commerce website. Let's say, some company like uh, like Zomato, right, or Food Panda. So, users, kind of write reviews around the restaurants, how was the food and all. And you might have seen that, so sometimes you might have seen the labels like, okay, it is written about, a particular type of food, a particular type of cuisine, that it was good versus it was bad, something was bad. So we are able to see that if we go into a restaurant, visit, kind of search restaurant zomato.com, there is always mention that okay, these are the particular cuisine types which are recommended by all of the users, and so on. So every review talks about something or the other, and so you can always classify, find titles of the documents, and that's what was a similar question of Pushpendra on implementing the topics, right? And okay, so let's move further. Uh, okay, so let us just quickly discuss around linear regression. I'm sure many of you have heard about linear regression because, and that's the reason you're here. And so I think this is always the topic 101, 101 kind of thing. So what we just discussed is y is equal to mx plus c, where here you are able to see, y dash is equal to mx. So here, interchangeably we also use weights. W1 is written y because it refers to weights, and x is x1 is the input variable with the features. Y is the label. Okay, B is a constant or bias. So we'll all do it in detail, but just think around that. Okay, very simply, our model is a linear regression model, wherein given a age of a particular, so think of x1 as a input factor in deciding whether the bank will offer you a loan or not. Let's say, given all the other features as constant, let's say age is the most important factor that is coming out while giving you a loan or not. So given x1 is the age, given so and so age, it based on that, this y dash will be decided. Okay, and so this line tells all that story. Think of it, it's not 100, 200 or 300, it's like 0 to, let's say, 80. 0 to 80, basically not even 0 to 80, but let's say 10 to 80, given that particular age, whether you are eligible for a loan or not. And so let's say it's a function of a linear line which says that, and think of, here actually it's a linear regression, so we would not actually go with the loan example. I think we should take a, let's say, an example of, given a certain age of a house, this is the price of a house. Okay, this is the age and this is the price. So as generally, as price is increasing, that would not be true in actual scenarios. Think of it as, like, say, age is decreasing. Let's say here it was 300, here it was 100, and so on. And so this would follow the regression line. What you can see is that you have to try, so these black points that you are able to see here, right, and all these points you are referring to what are the actual inputs. Okay, so basically a particular point like this, the black one, says that given this as age of the house, this should be the price, and so on. And so this is the error. Okay, and given this error, it is trying to fit the best line out of it, so that it can identify an equation out of it. Okay, so this is basically, just think of that, it will try to then predict it for completely new inputs. Let's say, given this age, how much would be the price. So it would say, okay, given this sorry, given this age, then the price would come out to be this by this model. But now let's move on further. Okay, so now this is a linear regression example. So let's say this is the size of the house and this is the price of the house. I think that would be a better example. And so now let's say this is the first model that we have fit, but these are the actuals, right? Now I want my model, so this is what is the error, right? So from here to here, this is think of it like this is error actually. Okay, now I want my model to predict, to learn it properly. So what I'll do, so it's basically what we call it as underfit, so it's not fit, and so it has high bias, right? And we, let's say, increase number of features or improve the features, let's say size and size square, and because it might be that my price is a function of not just size but size square as well. And so the moment I did this, it actually learned this, because the relationship was not, the relationship was of with the size square. Okay, and so, but then what happened, it learned it too much, so I mean it just learned, right? But let's say I increased more features, due to which what happened, that it tried to force fit with the whatever data points it have. And let's say tomorrow I have some new actual coming in, which happens to be here, but the error increased, right? Because I have tried to exactly pick up this exact points to learn so much that I have actually overfit on those points, right? In a way, basically I have overfit. And so which is something that, think of the scenario when, while we are learning, you know while we are learning anything, and we try to overlearn something, and which sometimes kills our creativity, because we just overlearned it, and so we are not able to kind of do that on a new concept, completely all new concepts. So rather than just learning concept, we learned exact values of an equation, which should not happen. And we always think that, okay, if even if it's new concept, we try to force fit there, but it actually is a new dynamics of the equation. So here as well, I know we are actually overfitting. So it's more general learning, it's more overfitting, and it's not the complete learning. So this is our different what happens when we try to train. So we might start with here, and we keep on training, and so it tries to learn, and as we keep training, sometimes the training error goes higher than the you know pre- prediction error. So which or the in this scenario, but and in this scenario, like, the new prediction error, the evaluation errors were all higher than the training error, where training error is very less, but the moment we predict something new, the error goes on that, on the new instances, becomes very high. So we need to ensure that we don't overfit our model, and also we need to ensure that we don't underfit our models. Okay, uh, so quickly, I'll see. Doesn't mean that we are covering linear regression here. So we have covered. We'll go through all the hands-on later on. We'll slowly and slowly increase the detailing and deep diving into each of these. I'm just covering quickly so that we can, we know what are the basics that should be learned, right? So loss functions. I'll not go in detail, but okay. So for example, for classification. So what is the loss functions? So anytime we are learning, we are learning from this to this, we basically ultimately want to reach here. So we have a loss function. We give our machine learning algorithm a loss function as an objective, that they have to minimize the loss. Okay, to do that, we have several metrics based on which it keep calculating the loss, and based on which it will keep trying to reduce it. We'll come to that as well, what is that algorithm. But the loss function is this. For classification, it's always about yes or no. Let's say whether it is a single one label classification or multi-label classification. Then different types of problems are there, but the log loss and cross entropy are the most used ones. So log loss is usually when there are two possible outcomes. Let's say given customer is coming onto your website, what is the likelihood that the customer will purchase? Given the certain recommendations to the customer, what is the likelihood that the customer will purchase a particular product? So you can have a log loss. Now, cross entropy is used when there are three or more possible outcomes. So it measures the performance of a classification model whose output value is probability value between 0 and 1. So cross entropy loss. So basically here, three or more possible outcomes are generally when you have actually multi classes. Um, for example, you can think of a scenario where you have, let's say, 10 choices in front of you, and you want to kind of let's say you show 10 products to your customer, and you build a classifier. What is the probability whether a first customer will purchase product 1, product 2, or product 3, and so on. So there are three three or more possible outcomes, right? and so that's where you can use cross entropy loss. Okay, we'll also pick up that problem statement as well soon, where we'll use softmax function in TensorFlow. We'll see that how cross entropy is used. And another type is hinge loss. Generally you might have, whosoever is not new to this machine learning, you might have heard about or read about hinge loss. Okay, so and there is another which is minimally used, at least I haven't used much, is exponential loss. And so okay, now coming to loss functions for regression. So the most prominently used are mean absolute error and mean square error. Sorry for the incomplete information here. I'll update these slides and the previous slide as well. Mean absolute error is something where you just say that okay, this is your predict the so x1 is your predicted, and not x1, let's say z1 is your predicted and y1 is your actual. And so z1 minus y1 is absolute, and coupled by mod or absolute, where you actually remove the sign, may becomes the mean absolute error, and then you divide it by basically the number of examples on which you have this. So that becomes a mean absolute error. But I mean, we'll see what are the scenarios where even you might have a confusion where you say that okay, no, when to use mean absolute error and when to use mean square error. But yeah, mean square error is something that uh, is average squared loss, for example, over the whole data set. So we'll go into detail around this, and uh, let's move further for now. Let me see if there are any questions. Okay, I don't see any questions anymore as of now. Maybe let me see, there are they on the dashboard. Okay, somebody asked that whether I need to watch previous video to watch this. No, it's not dependent, but it's recommended that if you watch that previous video as well, you will be able to will be using that somewhere in the one of the next lectures. So please watch that video as well. Okay, okay, fine, great. And let me go back. Fine. And okay, so now how we know that okay, while training a machine learning model, you know there we have to reduce the loss. But how to reduce the loss? What is that algorithm which helps us reduce the loss? So something like you might have heard about gradient descent. So this is the algorithm at the core. For now, just think of, I mean, the audience who is new to this. For you to simplify, just think that there is only one algorithm, gradient descent. Though there are many algorithms, and this is just one and the most basic one, but this is the right representation of understanding the concept. And so basically there are three variants of this algorithm. One is a batch, one is stochastic, one is mini batch. Let's discuss what it is. uh, so let's say, so this is the weights. Okay, this is the so let's say, taking the same example of given certain size, given the size of the house, and this is the coefficient, basically coefficient of the size of the house, and what is the loss of your predictions that your model is able to make, right? Given the historical data, it learned through all the historical data. Now while learning, you have your gradient descent algorithm is kind of trying to learn as much as from the data. And so this loss represents the difference in the predictions from the actuals and trying to minimize the error. Okay, so in the beginning it might have started from here, from this point, and uh, while it is trying to learn the weights of the equation, okay, the gradient descent helps to reduce the loss, and it always move in the negative direction towards the minima, loss minima. So we are assuming that our equation is a convex in nature. Our problem statement is convex in nature. That means it has just one global minima. Okay, so it will always be in this shape, and so the loss will keep decreasing. So what it is happening is that, let's say you start here, let's say you started here, and similarly you are here, and then you have the target here at this point, right? And so you keep moving towards this, but you have to take certain steps, but there are multiple directions, right, where towards towards how you will reach towards minima, the loss minimum. So that's where gradient descent helps you take steps. Now whether you take bigger steps, okay, or whether you take smaller steps is something that we'll discuss in the next slide. But what is, whether you want to speed it up in terms of, okay, for example, let's say you have 10,000 rows of data, just to be very small problem, 10,000 rows of data. Either you know learn 10,000, go over all the 10,000 rows and then update your weights, that is, which is change. So this grade update, I mean, with the help of this gradient, so gradient would be the delta, differential of loss with respect to the weights. Okay, differential of loss, that is a gradient. Okay, that is a slope. So whether you calculate this slope, what slope you need to move after going through all the data once and then update it, is a batch, or just taken one by one example and keep updating weights and keep moving. So that is stochastic, and that too randomly. Randomly pick one data point, second data point, third data point, and keep updating the gradient and keep moving in this direction. And what is more efficient after I mean, in real life, what is more efficient is always mini batch, where you don't say that you'll go over the whole class of the data set. Think of it, because while in real scenarios, I mean, in real scenarios, generally the data sometimes is not in thousands, right, but in lakhs or crores of rows, right? Then you cannot wait for your algorithm to go from whole of the data set and then move, right? Rather you will prefer to, and even going through one row might take your algorithm, might not take your algorithm in the most efficient path, and so you will take batches. You'll take certain batch of the data set, let's say a few hundred rows out of lakhs of rows, and so you'll learn those thousands of rows or hundreds of rows and update your gradient. The moment you calculate the gradient, you'll move accordingly. So you move here, okay, and okay, so and so on. So as the next slide says, it's all hyperparameter tuning practice. So I'm just, again, don't get worried from the whatever. If you're new, don't get worried from what are these and whether we are actually discussing in detail or not. We'll actually implement all this. We'll all use this. So just keep holding. We'll again come back to the basics in detail, but it's just to, so that at least you have a kind of look at what are the concepts that are being discussed here and important to learn. So this is as you can see, this is how we are we keep moving from here to here, here to here, and so we will reach here to the loss, minimal loss, right, efficiently. So to do that, there are certain factors which decide on that. Batch size, which we discussed, that okay, we need to, how big the batch we need to take to update gradient so that we can move in that direction. Okay, how slopey we want to, from here to here or here to here and so on. Epochs means how many number of steps. Let's say here 1, 2, 3. So these are 3 passes over the data set that we have gone and so updated our gradient. Okay, and learning rate. So learning rate says that okay, how fast we need to kind of learn the move these in this direction. So if the learning rate is high, then I'll keep moving faster and faster rather than I'll directly jump off here. Okay, so basically it becomes a multiplier to my gradient. So learning rate it's some is somewhere. So how I would in general or in real life scenarios I would want is I'll from here when I'm here I'll try to increase my learning rate which will directly take me here. From there I'll decrease my learning rate which will take me here. So I'll further decrease my learning rate in effort to so that I don't overshoot here. So I want from here to I want to reach here rather than from here to here, right? So I want to decrease my velocity of to moving towards my target of minimal loss. So I'll decrease my learning rate. So that's where learning rate is more as a tuning to gradient calculation. Okay, so these is all hyperparameter tuning. There are more hyperparameters, but these are the most common ones while doing this. Okay, so let's have a quick example. By the way, you don't need to use last. So the last lecture, basically, 1 weekend previous to the previous weekend, when Zimi took a lecture and helped you set up the cloud. In this lecture will not be using that as of now. So what you can do, I have shared this link. Please copy this link. By the way, let me post it somewhere. And are you able to? I hope you should be able to kind of see this link. And let me see how many of you are able to kind of see this. So this is the link. Please, you can always pick it from this slide, and let me put it here as well in speaker notes so that maybe you might be able to kind of do this. So basically this is the link you can open. Let me refresh it so that it comes to exact original face. So this is a collaborative environment by Google, so that we don't need to set up all this Jupyter notebook canned environment. Basically it's somewhere they have hosted and made it available for public reuse, and even the hardware at the backend. Of course, there's always a limit to this. Is all free, so don't worry about it, and you can do unlimited usage of it as per I know till now. And they have given a lot of examples here so that you can learn more from directly from here, and you can edit it as well, and then save it to drive and all. But as of now, let's focus on the implementation of the first step. So I would be waiting that is everybody able to kind of see this? Let me put this link there as well on the it is okay. So please go through this link and please open this link. Okay, and then let me come to this link. We are running short of time. We have 15 minutes, and I think we will be able to cover up quickly. So again, I would be just going quickly over it. We will again implement everything in detail. It is just to have a quick overview of so that you understand what is all there. It's not rocket science. It's just that you it's all always around standard, best practices that you should know over the time, that you will learn over the time. But okay, so let's see. So by the way, this is the example in TensorFlow. Okay, and so let's go. Uh, so let's first thing that we need to do. So there are two options here: connected on hosted run, connect to hosted runtime, and second option is to connect to local runtime. So don't go for connect to local runtime. I would say that park it for later. Just do connect to hosted runtime. So what actually it is doing is, it actually connects to some machine which is hosted by Google for you, and we can use it free of cost. So this is there as per their initiative to improve more research environment, collaborative environment, so that anybody can open it and start using it. Okay. So this is okay. Okay, so the first thing is, you know, you can also run your cell like this. The moment you hover it, you can just click here and your cell run. Or so, for example, so this is our text, right? And uh, sorry. So shift and enter also is a shortcut. At least I'm using Mac, so I'm able to do it. Shift plus enter. I don't know whether on it also runs to run this cell. So basically, it's a cell in the Jupyter Notebook. So Jupyter Notebook is an IDE. It's an integrated development environment. Like you might use Eclipse, or uh, maybe you might use Sublime Text, right, or Visual Studio Code, right. So similarly, it's a browser based IDE. So first thing that we will do is install the latest version of TensorFlow, but we will not do that. Let's stick to TensorFlow 1.8. The latest is 1.9, but let's stick to, let's change this and stick to 1.8, which is, I mean, 1.9 has recently come. I don't want to land up into issues, though it would be a stable release, but still, let's say, for anything that we'll do it on 1.8. Okay, till I actually inform you guys. So uh, let me install this. I hope this is already installed in this environment. So it says requirement already satisfied. So by default they have already, which is also written there in this machine, by default 1.8 was booted up. Okay. So another benefit that you are getting is it's all managed on cloud, so that you can go anywhere, and anywhere you can go and open it and practice. Okay. And then is the eager execution in this. So here you can see we are importing division and print function, and importing pyplotlib, matplotlib, basically from from matplotlib. So it's matplotlib is a data visualization library that we will use for our visualization perspective visualizations on the data. But let's go further. TensorFlow can be imported, like import TensorFlow STF, and also which is so TensorFlow, eager execution. So this is something that has come in recent versions of TensorFlow, which was something a very important feature, which was something missing. See, TensorFlow works on the concepts of graphs. Again, this is also be covered in the future sessions. But what happens is that it's graphs due to which the TensorFlow was not able to, do the immediate execution. So let's say I have written some operation, and then I want to immediately see the result. So I was not able to do that when eager execution was not available, unless I actually create a session out of it. So I mean, all these concepts, graphs and session, will be covered. So but eager execution enabled for an exploratory environment, that while on the go I'm writing, line by line, I should be able to execute and actually evaluate. So something like REPL, read, evaluate, print loop, right? The how the Python interactive, that how the Python users know. I think we the moment I write a line, I should be immediately able to execute. So not the this one, but the it's more around the operations or mathematical function, that what is the output given input. I should be able to actually see the output and make the output, rather than making it as tensors. Okay. And so it says that TensorFlow version 1.8.0 eager execution has been enabled. Okay, so tf.enable underscore eager underscore execution enables in eager execution. And so just to check tf.execute eagerly or not, yes, it says true. So, and the problem statement is a very, very famous problem statement. Again, the machine learning 101 kind of problem statement. So, think of it, you are a botanist and you want to build a application which should be supported by a model where it's supported by machine learning, and machine learning will help you build an algorithm where you given the certain inputs, so there are three species, Iris setosa, Iris virginica, versicolor, but all these classification you know that okay, if given the sepal and petals information, length and width, you will be able to classify these flowers, and so you collect all this information, and which the data is here. If you click iris flower dataset, you will find it. I mean, it's very, very popular. So what you have already have is that you measure the sepals and the petals and collect the data into an Excel sheet, let's say. Okay, and you store it here. Okay, let's say this iris training CSV. Let me show you as well. And so based on that, sepal length, sample width, petal length and petal width, based on these four features, you decide that what species it is. So that's where you'll be able to, your application will be able to classify and tell you, the moment you hover over this, it will calculate the length of the sepal and petal, and sepal and petal and width of the sepal and the petal, and it will tell you what species of the flower is this, and so on and so on. So, and that's where what you will do to so for that you need to build a model. And so let's build a model. And so you already have previously collected data from, let's say, some other botanists have already collected and built it for you, and the data set, so that you can train your model. And so you're able to see that okay, the data is residing here, so that you can train over it. So we will be using Keras here for quick explorations in TensorFlow. And so what the function is, tf.keras.utils.get file. So you download the file, and let's see, ran it. You can also run it from here, and then let's inspect it. Okay, what is the data it contains, how it contains the data. See, you have got to see four, or how many columns, 1 2 3 4 5, right? And so basically it contains 120 rows, 4 columns, and fifth as a decision parameter, whether it's status or versicolor or virginica. Okay, so this to this and this and this, these are sepal length, sepal width, and so on. Okay, these are the features, and this is a label saying, as you can see here, 0 for, if it is 2, that means it's virginica, if it is 1, it's versicolor, and if 0, it's setosa. Okay, the first line, as written here as well, the first line is a header containing information about the data. So 120 total examples. Each example has 4 features and 1 of 3 possible label names. Okay, so this is, so even, I mean, you can go I would recommend you go through the detail of ML terminology section of machine learning crash course. The link is also here. You can click on this, and you can go there and read about it. So this is all ML terminology that we discussed, but you can still read it through with the examples of the house pricing example, that, as you can see, right? So, but yeah, what is all these examples? Okay, no worries. Let's move forward. So now you have to build a input pipeline so that your model consumes the information from the CSV. So that's, and to do that, you need to decode, to provide the data so that the data is in ingested format, what to do when you start moving the data into the TensorFlow. You will know all these details why we need to do so, but when you are actually building production grade products, then you need to have all this. I mean, all these come in handy. So I have defined a function parse CSV. So basically this function gets input as each line of the CSV and does some processing over it. Think of like that. It reshape it, kind of put defaults if it is not available, decodes it and then reshape it, the structure, so that TensorFlow can consume it, and then finally breaks it up into features and label and returns features as well as label but separately. Okay, so now let's get on to I would say text line dataset. So all this will be used later on. So text line dataset is generally text files, reading data from text files. You'll say that okay, skip first one is the header, skip the header row, map parse CSV, parse each row, and we'll say randomize my data input and take batches. So remember batch size, so this is 32 I've taken, and so then iterate over batches one by one, and which provides back the let's say some example. Let's say it has provided some example TF tensor and so on, and label as 2 because eager execution is enabled, and so we are able to see actual values here. Otherwise we would not have been able to see that. I'll skip on this for now because there is a separate lecture onto that to explain that, but yeah. So now this is a model that we have built in Keras. So these are multiple so this is neural networks with 10 neurons, 10 neurons, and then 3 neurons. Okay, and there are 3 layers basically. And let's build it. So it's linear stack of layers. So as you can see, tf.keras.sequential is a linear stack of layers. Its constructor takes a lot of layer instances. So as written here, 2 dense layers with 10 nodes each, right? And an output layer with 3 nodes. So this is a 3. Why it is 3? Remember, we have 3 labeled variables: Setosa, versicolor, and virginica, right? So this correspond to, because our final output has to be in 3, and this 10 neurons takes input of 4 size. Why 4? Because we have 4 input features, right? As you can see here, 4 input features. Here it would be 10, 10, and then here 3, and so fine. So you can say that here it would be 3, so it is not shown in the right way, but exactly that way. But think of it like here, right? Or maybe actually use, these are 10, this is 10, and you can see 3 neurons here, 1, 2, 3. Okay, and then this becomes output here. And now again, training is a stage of machine learning when the model is gradually optimized and model learns a data set. The goal is to learn enough the structure of the training data to make predictions about unseen data. And we discussed about overfitting. So it's like memorizing the answers instead of understanding how to solve the problem, right? I mean, it's applicable to we humans as well as, right? Rather than learning the concept or rather than understanding how to solve the problem, we actually memorize the answers as well, which doesn't work when somebody when we go to the exam and then some completely new question comes in the exam which is not learned, and so it will not be able to bring good marks, right? And so on. So, and this is since labels are there 0, 1, 2, the iris classification problem is an example of supervised machine learning. The model is trained from example that contains labels. In unsupervised machine learning, the examples don't contain labels. Instead, the model typically finds patterns among the features, right? Okay, now here is a loss. Remember, we discussed loss and gradient. So this is a gradient descent function and this is a loss function. So we define what is loss for us. This is output and this is input, actual, basically actual output, and this is output but not actual but the predicted one based on model, and then we say this returns a loss. Now that loss is passed to this gradient function, so that we tell it that okay, this is my loss function, please optimized. Okay, so now we have defined it. So this is something like, you can, as you can see that there are multiple types of algorithms. So stochastic gradient descent is the red one. Remember, this is stochastic gradient descent. It is trying to kind of reach here, and the zero, ada grad, momentum, ada delta, RMS prop. So different have their own set of algorithm where, I mean, somewhere it is learning rate is constant, somewhere the learning rate also keep decreasing as you move towards minima, and so on. So we'll also cover these gradient descent algorithms, some of these, not all, and later less rest, you can always search and have a detail on it. The TensorFlow has many optimization algorithms available for training. You can click here and actually see that what are the algorithms implemented. This model used tf.train.gradient descent optimizer that implements stochastic gradient descent. Learning rate sets a step size to take for each iteration down the hill. This is a hyperparameter that we will comment it just to. Okay, so then I'll say tf.train.gradient optimizer descent optimizer, learning rate this, and it makes it a optimizer. Okay, now what is done is, now let's come on to the final thing where actually we run the training. So we take a list where we will store loss results, where we'll store accuracy results, so that we can later plot it via matplotlib. We set number of epochs is 201. 201 is like how many times I need to go over the passes of the data. Okay, one pass of the data, whether it is whole of the dataset, which is batch of the dataset, or whether it's one dataset, one data point, it's always considered number of epochs. So for epoch in range of number of epochs, so one iteration works over one dataset, whether it's a batch. So let's say here I say that okay, my tf.matrix.mean is considered as epoch loss average, and tf.matrix.accuracy says is a function for epoch accuracy. Let me go through xy over my trained dataset. So grade model, so basically I calculate the gradient given this model, given xy, I calculate my gradient, and then I do apply gradients, optimizer, do apply gradient, and this is passed here, and this model variables, right? And so this is a counter, more like a, so global step is equal to f.train get or create global step, as you might see. I think I mentioned it somewhere, but it's around, it's more like a, think around it as a counter that I've taken. Let me see if it is somewhere mentioned in detail. Otherwise I'll share that separately, or okay, anyways. So for your convenience, it's basically, if you search for it, it's a more like a global counter that you are keeping it here. Okay, so that you remember it across loops. Okay, so that your optimizer remembers it basically. Track progress. So now epoch loss average, remember. So you pass it the loss function at current batch loss. So you keep adding whatever loss was calculated, and so that you keep your track on what is the loss right now, and so on the accuracy. Okay, compare predicted label to actual label. So you keep comparing it to actual label, and so you keep for at each epoch you are actually storing the accuracy. Okay, and then you append these results into train loss results and train accuracy results, and you are, what is this, every 50 epochs you are printing the accuracy results and epoch. What is the epoch, what is the result or loss, what is the accuracy? Let us execute it and see. Epoch 0, it was loss as 1.49, accuracy was 35%, and see, after 50 epochs it immediately picked drastically reduced the loss, went up to 94%, and then 96, 97, 98, and 200 epochs it has, we have, because we have mentioned I think 201, so it actually went up to 200 epochs. Okay, and okay, so now visualize the loss function over time. It's important so that I can actually see only how many, I mean, if I'm fine with 94% accuracy, I don't need to go over. Let's say I might have given I have a question, right? I need to decide on how many epochs I need to run, because there is a cost trade-off to it. Why cost trade-off? I mean, think of, very big data set size, now I have to consume server cost, right? How much time I need to so it might be that after 97.5 I'm fine with this 97.5 accuracy, because beyond that with even 0.1% increase in accuracy will result in expenditure of lot of server cost. So I don't need that, right? My customers are fine with this accuracy, so why should I spend it, right? So ultimately, while you are building model, you also need to take into account whether investing in certain time of computation is actually worth spending or not. Okay, so this is where business decision comes into picture. Okay, and next is the matplotlib code. Though TensorBoard has a visualization tool altogether, we'll also discuss around it and we reach TensorFlow. But for now, since we have stored all this information, so you'll see your loss decrease like this as number of training. This is training loss, and see your accuracy jumped immediately from here. This is I think this is where you can stop, so right around, or maybe you might say that okay, your number of epochs, when it reaches around 60, your accuracy kind of gets saturated. So why to actually go beyond number of epochs 60, right? And so there is no point in doing that. And even after reducing the loss there, your accuracy is still in that range, so it's always good to kind of stop there, and so on. So then you can evaluate the model's effectiveness, uh, you know given this feature, this label, and the model prediction. So this is on the actual ones, the already training data set. If model prediction says so and your actual says so, and so you'll say, oh, why, then you will investigate further, why still it is not, either the actual label was wrong, you will actually investigate, by analyzing. That's something that's you have to put an analyst hat on your top and then see whether the actual model prediction is right, but or the actual label is right, I mean, whichever, and so on. And then you ask that, okay, now let me go to the field and actually collect the data, whatever new flowers that I have, so that I can actually you know kind of predict over them on the new data sets. And so let me do that, and I have basically ingested the new data set on which I have to predict and evaluate the test model. And let me see what, so these are basically, I'm basically taken the data set, test data set, and I've done the prediction. So model X, see, I have passed X input and I have prediction, Y is actual, and basically I've kept it just to I have just manually measured it as well, that okay, I know that okay, this is the flower, but I didn't took it inside the train while this data into while training. So just I have kept it separately so that I can actually measure whether the accuracy is actual accuracy or not, so whether this accuracy is visible or not. And so it gives 96.6% accuracy. Yes, and this was one instance. Now let's take, you know, I mean, more instances, completely new instances. Let's say this is this. Now my model is trained. I have these new instances that have come up, and let me do the prediction. Model predict data set, right? So I have converted this data into tensor, because TensorFlow needs tensor input. Okay, so we'll cover all this, don't worry about it. And see, so example 0, so we have taken 3 example. One is this example, and so example 0 prediction, I Satusa, and iris versicolor as the second, and the virginic as the third one. Okay, yeah. So I think today something was some that I wanted to discuss like this, around the predictions. Let me see if anybody have any question. Let me know if anybody has any question, then otherwise I will log off in a minute. or you can always ask the questions um, onto this, which is this one, I think. But you can always put your questions on YouTube video as well, which will be shortly available as a recording. and and we have a WhatsApp group, probably you can connect there as well. Okay, all right, I think we are done for today, and thanks everyone. It was great, having a conversation. Okay, so I think there is a question why there is no validation data. Yes, we do have. If we go back, remember this one. So this is validation data. Remember I told you that we have created a separate test set rather than a training set. I hope it is clear, Mukul. So this was a question from Mukul. Any other question? No? Okay. Thanks, Vishal. It was always, have always good to have a feedback. Guys, please provide the feedback on this as well. Mukul again has a question. That's great question. I have sometimes seen three set of data spread: training, validation, and test. Yes. So Mukul, you are right. So it's up to the user. We will do in the examples. So test is something that is always something that kept as completely separate. So in this scenario, if you see the last one, this one, right? So this is, they have taken as a test set. Okay, so this is, don't worry about this terminology. So logically they have taken it as a eval data set, so named it as test set. But in the setup of the notebook, they have done use it as eval data set. And so basically what is the concept, if we talk about, so there is training, valid, and test set. But here, I mean that doesn't matter actually, the naming terminology here. Just think of a concept that, okay, what they did was they took a training data set on which they learned the model, and then they use that test set to actually see, to validate their predictions. And then they actually, which Mukul is referring to as test set, and is actually right. He's actually right. And so this is completely, they don't know the predictions on it, but they don't know actuals on it. Although, I mean, we have taken a separate, we have taken it separately, saying that, okay, this is where I need to predict. So I don't have label for it. So I just predict it, right? And so on. So when we will implement, Mukul, when we will implement the whole algorithm in TensorFlow, we will have training and validation data sets on the fly, where the model will keep learning and keep adjusting accordingly in the case of TensorFlow. And then we'll have a test set separate, where we'll actually try to predict. Well, we don't have actuals, right? Think of it that you have hidden the test set somewhere else, so that you don't know actuals, but you still need to validate on test set for the for your business stakeholders to showcase, right? So that's it. Okay, thanks. Any more questions? I would love to answer that. Otherwise I'll kind of sign off. Any other feedback, please put it here.